Hello. In the last two of these videos, we have talked about the Carnot cycle. In doing so, we have seen how we can create a universal calibration for temperature by considering the operation of the Carnot cycle. In those videos, I explained how a Carnot cycle can be used to describe the set of transitions that take place in a particular special type of engine. I explained how these engines are driven by the changes in state that happen in the gas inside the pistons within them. Furthermore, I told you about how the gas inside these pistons was a one-component, one-phase system whose state of equilibrium, in accordance with Gibbs phase rule, can be characterized using two thermodynamic variables only. Throughout the previous videos, I used the pressure and volume to characterize the state of the gas in the piston. I thus drew out our thermodynamic cycle on the PV plane and explained how the system, on completion of a cycle, returns to the initial thermodynamic state. In terms of the operation of the engine and the set of transitions inside them, I said there were four stages. During the first of these stages, the engine is placed in contact with a heat bath, and the gas is expanded isothermally, i.e. at constant temperature. During the second stage, the heat bath is removed, the system is thermally lagged, and the gas is expanded adiabatically. During this second step, the thermal lagging prevents heat from being exchanged with the surroundings, and thus the temperature of the gas drops. In the third step, the system is placed in contact with a heat sink, and the gas is contracted isothermally. The heat sink is then removed, the thermally lagging is placed around the system once more, and the system is compressed adiabatically so that the temperature of the gas increases. In this video, I am going to focus on the adiabatic compression and adiabatic expansion stages of the engine's operation. These transitions are interesting because the system is thermally lagged during these parts of the cycle. As such, the system is not allowed to exchange heat with its surroundings. The important thing to remember when considering these parts of the cycles is that the thermal lagging does not prevent the temperature in the gas from changing. As the gas expands, its temperature will drop, and as it contracts, its temperature will increase. Temperature is not a measure of the amount of heat in the system. In fact, there is no such thing as a measure of the amount of heat in the system. Heat is something that is always passed between phases. It is not a property of the state of the system. The other important thing to remember as we go through this video is that the expression that I am going to derive for the work done during these two stages of the engine's operation is not an expression for the total work done by the engine. Work will also be done during the isothermal expansion and isothermal contraction stages of the engine's operation. With all this in mind, let's begin. In my first of these videos on the idea of work and heat, I explained how the 19th century physicists who developed the thermodynamics established that there must be more going on in engines than just the expansion and contraction of gas in the cylinders. In that video, I explained that these guys concluded that there must be some extensive variable other than volume that characterizes the state of the system, and this extensive variable must have something to do with the transfer of heat between phases. What makes the adiabatic expansion and contraction stages of the Carnot cycle's operation interesting is that no heat is transferred. Consequently, during the adiabatic expansion stage, shown here, the state of the system changes as shown here. The only thing that happens is that the volume increases. Our mysterious extensive variable that has something to do with the transfer of heat does not change. Similarly, during the adiabatic contraction stage shown here, the only thing that happens to the gas inside the cylinder is that its volume decreases, as shown here. Once again, our mysterious extensive variable that has something to do with the transfer of heat does not change. The fact that only the volume changes during these stages, and that other extensive variables do not change, is useful if we now think about the work that the engine does on the universe during these stages. Remember that this is the work the engine does to lift things, drive cars, and so on and so forth. We know from Newton's third law that if the engine does work on the universe, then the universe must do work on the engine. As the volume of the gas changes, this work done by the universe on the engine must act to change the volume of the gas only. Let's now simplify our engine down a little so that we can understand these ideas a little better. What we will suppose is that we have the gas in the bottom of the piston as shown here. We will have the thermal lagging, shown in red, so as to prevent any transfer of heat between the gas and the surroundings around our piston. We then have a heavy piston head, shown as a blue square on this diagram, that will be pulled down by gravity. In other words, the piston head will have a force acting on it due to gravity, and this force will act on the gas. Let's now suppose that during the adiabatic expansion phase, this heavy piston head is pushed upwards by an amount delta x. The gas will do the amount of work shown here in order to push the piston head upwards like this. Notice also the minus sign here is required because the piston head is being pushed in the opposite direction to the direction in which the force is pointing. I now recall that pressure is defined as force divided by area. In this case, I could thus rewrite the force F acting on the gas by multiplying the pressure the piston head applies to my gas by the area of the head of the piston that is in contact with the gas. This allows me to rewrite my expression for the work done in pushing back the piston head as shown here. The final stage comes when I recognize that if I multiply the area of the piston head by the dx, the distance it will be pushed back, I get the change in the volume of the gas. I thus arrive at the following expression for the work done in pushing back the piston head. The work transferred from the gas to the universe is just equal to minus the integral over the change in the volume, minus the integral over the change in volume of the pressure. Let's finish by briefly summarizing what we have learned from this video. We have arrived at the following expression that tells us that we can calculate the work done by a gas when it expands by using the following integral over the change in volume. We integrate over an extensive variable, in this case v, that describes how much the state of the system changes during the transition. The integrand in this expression is an intensive variable, in this case the pressure, that tells us how the system is coupled to the environment. Performing this integral allows us to find the amount of work that the universe has done on the system in changing the system state. The key thing to remember about this expression, however, is that it only holds if our change of state has taken place adiabatically. Remember, an adiabatic transition is one in which only the volume of the system changes. The as yet mysterious extensive thermodynamic variable that is related to heat in some way remains fixed throughout the transition because in the derivations in this video the system was thermally lagged so that heat could not pass between the system and the environment. In the next and final video on the Carnot cycle, we are going to reveal what this mysterious extensive thermodynamic variable that is related to heat in some way is. I hope that I'm not ruining things for you and ruining the surprise by telling you that it's the entropy. Thank you for your attention.